So far, we can see that the theory of calculus on real numbers are of sound foundation. Next, we'll use representation of Cauchy sequence to define Euler's number e and its exponential function e to x. It's easy to show that a series of inverse factorials is Cauchy, and we call the limit as e. And the e can also be defined as the limit of continuous compounding interest, which says that e equals the limit of nth power of 1 plus 1 over n when n goes infinity. This formula is very useful in proving laws of large numbers. And the exponential law is defined as e to x equals the infinity sum of x to n over n factorial. And the convergence is valid for all x in R. Since the denominator n factorial decays much faster than power of x, we can exchange the derivative with summation and get the result that the derivative of ex is itself. And in other words, e to x is an eigenvalue of derivative. And that's why the exponential function is so important in theory of differential equations. And that's what about the limit. From now on, we'll move our focus from numbers to functions. In this section, we'll show the power of geometric method by solving a problem about continuity. And then we'll have a tour from derivative to Tennant's expansion. The geometry of a function can be graphically shown as a curve in the two-dimensional plane. Through a continuous f, AB on x-axis is mapped to CD on y-axis. Problem is, can we prove that for all continuous functions, the image is always a bounded closed interval? The proof would be non-trivial without using topology, which is a branch of geometry focusing on global invariance and transparent. And there's a counter-Dedekind axiom states that R is isomorphic to a direct line, and hence R gains the topology induced by the open line segments. And as a result, there are two definitions of continuity for a function f, one by limiting and one by topology. The continuity definition in calculus basically says that we can exchange the order of limiting and function evaluation. And the continuous in topology says that f is continuous if for arbitrary u open in R, the inverse image is also open. And this theorem states that these two kinds of continuity are equivalent. And here's the proof of the theorem to show flavor of epsilon delta in use. In the proof, we'll also use the fact that if x is an inner point of an open set U, then you can always find an open ball centered at x, which is a subset of U. And since continuity in calculus is equivalent to continuity in topology, we can also solve the problem using geometric methods. Here's a flow map of proof. We have used two topological properties of the interval AB, which are compactness and connectedness, 紧致性、连通性, both preserved and continuous map. Thus, the image FAB is also connected and compact. Hence, it's a bounded closed interval CD. End of the proof. And a useful corollary is that continuous map on bounded closed interval can always realize the maximal and the minimal value. And we'll use it later. Next, we'll begin our tour to Taylor's expansion starting from geometry of derivative. For a smooth curve, the tangent line can be defined as the limit of secant lines. If the curve can be parametrized by a function f, the equation of secant line can be written as follows, and we should focus on the slope. When Qn approaches P, the slope will converge to the derivative of f at x0. So the geometric meaning of derivative is the slope of the tangent line, and it can be shown that the tangent line is the best linear feet of the curve near P. The relationship between derivative and curve can be generalized to higher dimensions. For a curve embedded in Rn, let gamma be a smooth curve passing point P. Then the derivative of gamma in Rn gives the tangent vector of M at P. Obviously that the tangent vector is not unique, and all tangent vector at P spans a hyperplane in Rn called the tangent space of M at P. And the picture shows a special case of the curved curve M in R3. And if it can be parameterized as z equals fxy, then the two base vectors of the tangent space and the normal vector can be easily derived by computing the derivative of GARM and the local coordinates. And like tangent line is the best local linear feet of curve, the tangent plane is M, the best linear feet near P. Geometrically, integral can be treated as the signed error between curve function and the x-axis. By chopping the graph along the y-axis, the integral domain AB is split into small pieces. On each piece, the curve is approximated by a rectangle, whose height is the sampled value along the curve. Sum of all rectangle errors are called Riemann sum. If independent of choice of sampling, Riemann sum converge when the maximum ones of small pieces approach zero, we say f is Riemann integrable on AB. It could be proved that the Riemann integral function is piecewise continuous on AB, and the site of discontinuity point is countable. The choice of psi I, however, do affect the precision of numerical integral. Using Taylor's expansion, we can estimate the error of different Riemann sums. For left and the right Riemann sum, we have an error of order h. And for midpoint Riemann sum, we have an error of order h squared, which is bad. But in practice, topoloidal Riemann sum are more often used since it's more computation efficient than middle point, but with the same level of error. And with integral, we can define norm on space of functions. And we have LP norm for finite p as the p root of integral of f absolute value to p. And I will also have the L infinity norm defined as the supremum of absolute value of f. And since uniform convergence is equivalent to L infinity convergence, the uniform convergence theorems can be rephrased as intrinsic properties of function space CAB with L infinity norm. The function space CAB is the algebra of continuous functions on AB. Then we have first, CAB is a complete matrix space with L infinity norm, which says that for a uniform convergent sequence of continuous functions Fn, the pointwise limit is also continuous. And the operation of L infinity limit can interchange with integral on CAB, which says that for Fn, the integral of limit equals the limit of integral. A similar study can also be done on space of Riemann integrable functions. And also, the round R is also complete and L infinity norm and admits in interchange of limit and integration. It turns out that L infinity is too strong for some functions. Consider the example in the green box. For x in 0 to 1, Fn is defined as x squared over x squared plus square of 1 minus nx. It's easy to show that Fn converges pointwise to 0, and the integral converges to 0 too. So we can interchange limit and integral and the pointwise convergence. But Fn is not F infinity quotient, since there's a point for each Fn with valued to 1. Thus, there's no limit in R for Fn, and the interchange of L infinity limit and integral is invalid. To keep interchange of limit and integral, we can relax L infinity to L1. And the L1 norm Fn did converge to 0, thus interchange of limit and integral becomes valid. However, relaxation of norm comes with price, and it turns out R is not complete and L1, which is bad. So we find another integral called the bigger integral.